September 15th, 1940, 11:30 hours, 26,000 feet above the English Channel. Flight Lieutenant Brian Carberry rolled his Supermarine Spitfire Mark I into a climbing turn that defied everything German fighter pilots had been told about British aircraft capabilities. Below him, Hauptmann Helmut Wick's Messerschmitt Bf 109. Emil struggled to match the Spitfire's rate of climb, its Daimler-Benz engine straining against the thin air at maximum combat power. What Wick was witnessing violated fundamental assumptions about aerial combat that had shaped Luftwaffe fighter doctrine since the Spanish Civil War. German pilots had dominated European skies for 3 years, using superior tactics and aircraft performance. The Messerschmitt Bf 109 had outclimbed and outmaneuvered every opponent from Poland to France. Yet this British fighter, dismissed by German intelligence as an obsolete biplane derivative, was climbing away from Germany's most advanced interceptor with ease that bordered on the impossible, 6,000 feet per minute. The Spitfire's rate of climb exceeded published performance specifications for the Messerschmitt by a margin that German engineers had declared technically unfeasible. Carberry's aircraft gained altitude faster than any fighter Wick had encountered during 3 years of combat operations. Within 90 seconds, the Spitfire had climbed 3,000 feet above the laboring Messerschmitt, achieving the altitude advantage that determined victory or defeat in aerial combat. This was the moment when German confidence in their technical superiority began to crack. For the first time since the war began, Luftwaffe pilots faced an opponent that could outperform their best aircraft in the most critical aspect of fighter combat. The psychological impact would prove as significant as the tactical implications. The aircraft they had mocked as obsolete British engineering was about to change the course of the air war over Europe. The story of how the Supermarine Spitfire transformed from a laughingstock to a legend doesn't begin with engineering excellence. It begins with German arrogance, flawed intelligence, and fundamental misunderstandings about British aircraft development. To understand why the Spitfire's climbing performance came as such a shock to German pilots, you must first understand what they believed about British aviation and why those beliefs proved catastrophically wrong when war arrived. In 1936, when the first Spitfire prototype took flight from Eastleigh Aerodrome near Southampton, German aviation experts dismissed British fighter development as hopelessly backward. Luftwaffe intelligence reports described Royal Air Force fighters as outdated biplanes, unsuitable for modern warfare. The dominant British fighter, the Gloucester Gladiator, reinforced these assumptions with its fabric-covered wings and fixed landing gear. German observers at international air shows during the late 1930s noted British aircraft with undisguised contempt. Aviation magazines published in Berlin described Royal Air Force equipment as representative of an empire in decline, unable to adapt to the realities of mechanized warfare. German pilots trained with confidence that they would face minimal opposition from British fighters when war came. The Messerschmitt Bf 109 had established German confidence through a series of impressive victories during the Spanish Civil War. Flying with the Condor Legion from 1936 to 1939, the aircraft had destroyed hundreds of Republican fighters with minimal losses. German pilots returned from Spain convinced that their tactics and technology represented the pinnacle of military aviation. Willy Messerschmitt's design incorporated every lesson learned from Spanish combat operations. The aircraft featured a low-wing monoplane configuration with retractable landing gear and an enclosed cockpit. The Daimler-Benz DB601 engine provided exceptional power-to-weight ratio and high-altitude performance. Most importantly, the aircraft could climb at over 4,000 feet per minute, enabling German pilots to achieve superior altitude before engaging enemy fighters. The psychological advantage proved as important as technical performance. German fighter pilots entered World War II believing they flew the world's most advanced combat aircraft. Their training emphasized the superiority of German engineering and tactics. Luftwaffe doctrine assumed that enemy fighters would be inferior in all respects, and could be defeated through standard procedures developed during Spanish operations. British aircraft development during the late 1930s followed a completely different philosophy that German intelligence failed to understand. While Germany focused on proven conventional designs, British engineers pursued radical innovations that pushed the boundaries of aeronautical science. The Air Ministry specification that led to the Spitfire demanded performance levels that required revolutionary approaches to aircraft design. Reginald Mitchell, chief designer at Supermarine Aviation Works, approached the fighter requirement with unconventional thinking that German engineers had rejected as impractical. Instead of simply scaling up existing designs, Mitchell created an entirely new configuration, optimized for high-speed flight and exceptional maneuverability. The elliptical wing shape that became the Spitfire's signature represented mathematical precision in aerodynamic design. The wing design incorporated advanced concepts that German engineers considered too complex for practical application. Mitchell used variable wing thickness and sophisticated airfoil sections that optimized lift distribution across the entire wingspan. The elliptical planform minimized induced drag while maximizing structural efficiency. German intelligence observers dismissed these features as unnecessary complications that would prove unreliable in service. More critically, German analysts misunderstood the significance of the Rolls-Royce Merlin engine that powered the Spitfire. While German engines emphasized reliability and ease of maintenance, the Merlin represented a different approach that prioritized performance above all other considerations. The British engine incorporated advanced metallurgy and precision manufacturing that enabled power outputs German engines could not match. The Merlin's supercharger system proved particularly innovative. Unlike German engines that used single-stage supercharging, the Merlin employed sophisticated boost control that maintained power output at high altitudes. This gave Spitfires a decisive advantage in the thin air above 20,000 feet, where most combat occurred. German engines lost power rapidly as altitude increased, while the Merlin maintained performance throughout its operational envelope. British manufacturing techniques also differed significantly from German methods. Supermarine employed stressed skin construction that distributed structural loads throughout the airframe, rather than concentrating them in a central framework. This approach produced aircraft that were both lighter and stronger than conventional designs. German engineers had experimented with similar techniques, but abandoned them as too difficult to manufacture reliably. The production challenges proved considerable. Building Spitfires required precision manufacturing capabilities that few aircraft companies possessed. The complex wing shape demanded specialized tooling and skilled craftsmen who could work to tolerances measured in thousandths of an inch. Early production proceeded slowly as workers learned new techniques and manufacturers developed appropriate equipment. German intelligence reports from this period consistently underestimated British production capabilities. Luftwaffe analysts assumed that the complex Spitfire design would prove impossible to manufacture in significant quantities. They predicted that any war would end before British industry could produce meaningful numbers of advanced fighters. This fundamental miscalculation would prove costly when combat began. The first production Spitfires reached Royal Air Force squadrons in August 1938, just as European tensions approached the breaking point. No. 19 Squadron at RAF Duxford received the initial delivery of aircraft and began working up to operational status. German intelligence monitored these developments but failed to grasp the significance of what they observed. The transition from prototype to production aircraft involved overcoming manufacturing challenges that German observers dismissed as insurmountable. Supermarine's production facility at Southampton required complete reorganization to accommodate the precision manufacturing demands of Spitfire construction. Traditional aircraft assembly methods proved inadequate for the complex wing structures and advanced systems that Mitchell's design required. Early Spitfire operations reinforced German misconceptions about British fighter capabilities. The aircraft experienced numerous technical problems during initial service introduction. Engine reliability proved problematic, with frequent failures requiring emergency landings. The complex retractable landing gear system suffered repeated malfunctions. Gun installations required extensive modifications before achieving reliable operation. German observers interpreted these problems as confirmation of their assumptions about British engineering inadequacy. Intelligence reports emphasized the mechanical failures while ignoring the underlying performance capabilities that would prove decisive in combat. Luftwaffe planners assumed that technical problems would prevent effective Spitfire operations during wartime conditions. As the Battle of Britain approached during summer 1940, German confidence remained unshaken. Luftwaffe intelligence estimated that the Royal Air Force possessed fewer than 700 modern fighters, most of them inferior to German aircraft. German pilots expected to achieve air superiority over Britain within weeks of beginning sustained operations. The reality proved dramatically different. When large-scale air operations began in July 1940, German fighter pilots encountered Spitfires in significant numbers for the first time. The initial engagements provided shocking revelations about British fighter capabilities that contradicted everything German intelligence had predicted. The first major air battle occurred on July 10, 1940, when 70 German aircraft attacked a British convoy in the English Channel. Royal Air Force fighters scrambled to intercept, including Spitfires from No. 5 Squadron led by squadron leader James Leithart. The engagement that followed would shatter German assumptions about British fighter performance. The German formation approaching the Channel convoy consisted of Dornier Do 17 bombers from Kampfgeschwader 2, escorted by Messerschmitt Bf 109 fighters from Jagdgeschwader 26. The mission represented a standard operation designed to test British defenses and inflict damage on British shipping. German commanders expected minimal opposition from Royal Air Force fighters based on intelligence assessments of British capabilities. Leithart's Spitfires climbed to intercept the German formation at 18,000 feet. The Messerschmitt Bf 109 escorts, confident in their altitude advantage, dove to engage the British fighters. What happened next defied German expectations completely. The Spitfires not only matched the Messerschmitt climb rate, but actually outclimbed the German fighters by a significant margin. Hauptmann Hannes Trautloft, leading the German fighter escort, later described his shock at watching British fighters climb away from his formation despite starting from a lower altitude. The Spitfires gained height faster than any fighter he had encountered during 3 years of combat operations. Within minutes, the British aircraft had achieved superior altitude and were diving to attack from above. The tactical implications proved immediate and decisive. German fighter tactics were based on maintaining altitude advantage through superior climbing performance. When this fundamental assumption proved false, established procedures became not only ineffective, but dangerous. German pilots found themselves fighting from disadvantaged positions they had never trained to overcome. The immediate tactical response by German pilots reflected confusion and disbelief at encountering aircraft performance that contradicted fundamental assumptions about British capabilities. Hauptmann Wilhelm Balthasar, leading the second Gruppe of Jagdgeschwader 3, reported that his formation's standard climbing attack was easily countered by Spitfires that gained altitude faster than any aircraft his pilots had previously encountered. Individual German pilots developed personal techniques for surviving encounters with Spitfires based on their aircraft's remaining advantages and their own flying skills. Oberleutnant Joachim Müncheberg discovered that his Messerschmitt retained superior diving acceleration that could be exploited in specific tactical situations. However, these advantages required precise timing and favorable circumstances that proved difficult to achieve consistently. The energy management techniques forced upon German pilots by Spitfire superiority fundamentally altered Luftwaffe tactical doctrine. Pilots learned to conserve altitude and speed advantages whenever possible, avoiding turning engagements that would allow British fighters to exploit their climbing capabilities. The tactical modifications required situational awareness and discipline that many experienced pilots found challenging to master. Flight Lieutenant Johnny Kent, commanding No. 92 Squadron during critical Battle of Britain engagements, developed tactical procedures that maximized Spitfire climbing advantages against German formations. His squadron's success rate against Messerschmitt fighters exceeded average Royal Air Force performance by significant margins through systematic exploitation of aircraft superiority. The combat effectiveness achieved by experienced British pilots flying Spitfires demonstrated the multiplicative effect of superior aircraft performance combined with appropriate tactical employment. Squadron leader Douglas Bader, despite his physical disabilities, achieved exceptional success rates by using Spitfire climbing performance to control engagement conditions against German fighters. German formation leaders attempted to compensate for aircraft performance disadvantages through numerical superiority and coordinated tactics. However, the fundamental limitation of being outclimbed by opposing fighters prevented effective implementation of traditional German tactical procedures. Luftwaffe formations found themselves consistently fighting from positions of disadvantage. The Spitfire's climbing performance derived from the combination of advanced aerodynamics and engine power that German engineers had failed to achieve. The elliptical wing design provided exceptional lift-to-drag ratio that enabled rapid altitude gain. The Rolls-Royce Merlin engine maintained power output at high altitudes where German engines began to lose effectiveness. The aerodynamic efficiency of Mitchell's elliptical wing design exceeded German understanding of theoretical aerodynamics. British engineers had achieved practical application of mathematical principles that German aerodynamicists considered too complex for operational aircraft. The wing's variable thickness distribution and sophisticated airfoil sections optimized lift generation across the entire wingspan. The manufacturing precision required to build elliptical wings to design specifications exceeded German production capabilities significantly. British craftsmen achieved tolerances measured in thousandths of an inch while maintaining production schedules that supported wartime requirements. The combination of theoretical sophistication and manufacturing excellence proved impossible for German industry to replicate. More importantly, the Spitfire's rate of climb increased with altitude rather than decreasing like conventional fighters. At 25,000 feet, where most combat occurred, the aircraft could climb at over 5,000 feet per minute. This exceeded the performance of any German fighter by a margin that proved tactically decisive. The high-altitude performance characteristics of the Merlin engine provided Spitfires with decisive advantages in the thin air where most aerial combat occurred. The sophisticated supercharger system automatically adjusted boost pressures to maintain sea-level power outputs at altitudes where German engines lost effectiveness rapidly. The technological sophistication exceeded German engineering capabilities by several years of development. Fuel injection and mixture control systems developed specifically for the Merlin engine enabled optimal performance under varying flight conditions that German pilots could not match. British engine designers achieved precise control over fuel delivery and combustion that maximized power output while maintaining reliability under combat stress. The technical sophistication exceeded German power plant technology significantly. German pilots initially attributed Spitfire climbing performance to luck or exceptional pilot skill. Luftwaffe intelligence maintained that British fighters could not consistently outperform German aircraft. Only after repeated encounters confirmed the pattern did German commanders acknowledge that they faced a fundamental technological challenge. The systematic documentation of Spitfire performance advantages through multiple combat encounters provided undeniable evidence that German intelligence assessments had been catastrophically wrong. Combat reports from experienced pilots, gun camera footage, and technical analysis of recovered aircraft components confirmed British technological superiority in critical performance areas. Hauptmann Helmut Wick, one of Germany's most successful fighter pilots, filed detailed combat reports documenting Spitfire performance that exceeded German aircraft capabilities by margins he had previously considered impossible. Wick's technical background enabled precise assessment of British aircraft performance that influenced subsequent German tactical development. The psychological impact on German fighter pilots proved as significant as the tactical disadvantage. Luftwaffe training had emphasized German technical superiority as the foundation of combat effectiveness. When this assumption collapsed, pilot confidence began to erode. German fighters that had dominated European skies suddenly found themselves outclassed by opponents they had dismissed as inferior. Individual pilot reactions to British technological superiority varied based on experience levels and personal characteristics. Veteran pilots who had achieved success against inferior opponents struggled to adapt to situations where their aircraft were outperformed. New pilots entering combat faced additional challenges of learning tactics designed to compensate for technological disadvantages. The confidence crisis affected German aircrew performance in ways that extended beyond immediate combat effectiveness. Pilots reported increased stress levels and psychological fatigue during missions over British territory. The constant awareness of fighting with inferior equipment created mental burdens that degraded decision-making during critical moments. Squadron commanders throughout the Luftwaffe implemented counseling programs and morale-building activities designed to address the psychological impact of technological inferiority. However, these measures could not eliminate the fundamental reality that German pilots were flying aircraft that could not match British performance in areas critical to aerial combat success. Oberst Adolf Galland, one of Germany's most successful fighter pilots, later described the shock of first encountering Spitfires over southern England. His Messerschmitt Bf 109, which had easily defeated French and Polish fighters, struggled to match British climbing performance. For the first time in his combat career, Galland found himself fighting from a position of disadvantage. The technical analysis of captured Spitfire components provided German engineers with additional surprises. The sophisticated manufacturing techniques and advanced materials exceeded German expectations by considerable margins. British industry had achieved production standards that German factories could not match, despite years of rearmament efforts. The Rolls-Royce Merlin engine particularly impressed German technical experts. Detailed examination revealed metallurgical advances and precision manufacturing that German engine manufacturers had been unable to achieve. The supercharger system incorporated design features that German engineers immediately recognized as superior to their own approaches. German attempts to counter Spitfire performance through tactical modifications proved largely unsuccessful. Luftwaffe fighter units adopted new formations and engagement procedures designed to minimize the impact of British climbing advantage. These measures reduced German losses but failed to restore the decisive superiority that had characterized earlier campaigns. The tactical modifications implemented by German fighter units during August and September 1940 reflected desperate attempts to adapt doctrine developed for superior aircraft to situations where German fighters were comprehensively outperformed. Jagdgeschwader commanders experimented with different formation structures, altitude deployments, and engagement procedures that might compensate for technological disadvantages. Major Werner Mulders, commanding Jagdgeschwader 51, developed alternative tactical approaches that emphasized hit-and-run attacks rather than sustained engagement with British fighters. His pilots learned to use superior diving speed and initial acceleration to attack British formations quickly before disengaging. However, these tactics provided limited effectiveness against Spitfires that could climb away from pursuing German fighters. The psychological impact of fighting against superior aircraft affected German pilots in ways that extended beyond immediate combat performance. Aircrew reported increased stress levels and fatigue during missions over British territory. The constant awareness of technological disadvantage created mental burdens that degraded decision-making and situational awareness during critical combat moments. The development of improved German fighters proceeded slowly due to resource constraints and technical limitations. The Messerschmitt Bf 109F model, introduced in early 1941, provided better high-altitude performance but still could not match Spitfire climbing capabilities. German industry lacked the manufacturing capacity and technical expertise to produce competitive aircraft quickly. Meanwhile, British Spitfire development continued advancing at a rapid pace. The Mark V variant, introduced in early 1941, incorporated a more powerful Merlin engine and improved aerodynamics that further enhanced climbing performance. German pilots found themselves facing increasingly capable opponents as the war progressed. The continuous improvement program implemented by Supermarine and Rolls-Royce ensured that British technological advantages were maintained and extended throughout the conflict. British engineers systematically analyzed combat reports, incorporated lessons learned from operational experience, and implemented design modifications that addressed specific performance requirements identified through actual combat operations. The strategic implications of Spitfire superiority extended throughout the European theater. German bomber formations required larger fighter escorts to provide adequate protection against British interceptors. This reduced the number of bombers available for offensive operations and increased fuel consumption for extended escort missions. Luftwaffe fighter units suffered increasing casualty rates as the technological balance shifted against German aircraft. Experienced pilots were lost faster than replacements could be trained, degrading overall unit effectiveness. The qualitative advantage that had enabled small German forces to defeat larger opponents gradually disappeared. The Battle of Britain marked the first major German defeat of World War II, and Spitfire climbing performance played a crucial role in achieving British victory. German bombers found themselves under constant attack from fighters that could climb to intercept faster than escort aircraft could respond. The sustained losses forced Germany to abandon daylight bombing operations over Britain. Hermann Göring, commanding the Luftwaffe, initially refused to accept that German fighters were technically inferior to British aircraft. He attributed pilot reports of superior Spitfire performance to cowardice or incompetence. Only after reviewing combat films and examining captured aircraft did Göring acknowledge the magnitude of the technological challenge. The impact on German pilot morale proved lasting and significant. Fighter pilots who had entered the war confident in their equipment superiority found themselves questioning fundamental assumptions about German technical capabilities. Combat effectiveness declined as pilots adopted more cautious tactics to avoid confrontations they might not survive. British pilots, meanwhile, gained confidence from their aircraft's superior performance. Royal Air Force fighter squadrons developed increasingly aggressive tactics that exploited Spitfire climbing advantages. The psychological balance shifted decisively in favor of British forces as German air superiority evaporated. The technical lessons from early Spitfire encounters influenced German aircraft development throughout the war. Engineers attempted to incorporate British design features into new German fighters, but manufacturing limitations and resource constraints prevented effective implementation. Germany never regained the technological edge that had characterized early war operations. The comprehensive technical analysis undertaken by German engineering teams following the capture of intact Spitfire aircraft revealed design innovations that exceeded German capabilities in multiple critical areas. The examination process involved systematic disassembly of complete aircraft, detailed measurement of components, and metallurgical analysis of materials that provided unprecedented insights into British manufacturing techniques. Professor Ernst Heinkel, founder of Heinkel Flugzeugwerke, personally supervised the technical evaluation of captured Spitfire components and declared British manufacturing standards superior to German production capabilities in virtually every measurable category. His detailed report to the Reich Air Ministry acknowledged that German industry had fundamentally underestimated British technological achievements. The metallurgical analysis conducted by German materials scientists revealed aluminum alloy compositions and heat treatment processes that exceeded anything achieved by German manufacturers. British metallurgists had developed specialized alloys with strength-to-weight ratios that enabled aircraft construction techniques impossible with available German materials. The technological gap in basic materials science proved impossible to bridge quickly. Wind tunnel testing of Spitfire wing sections conducted at German research facilities confirmed the aerodynamic superiority of the elliptical planform design. German aerodynamicists calculated that the British wing design achieved lift-to-drag ratios approximately 15% better than comparable German wing configurations. The mathematical precision of Mitchell's design exceeded German theoretical understanding. The examination of Rolls-Royce Merlin engines provided German engineers with detailed documentation of British power plant technology that surpassed their previous comprehension. The precision manufacturing standards, advanced materials, and sophisticated control systems incorporated in the Merlin exceeded German engine capabilities by margins that would require fundamental changes to German industrial processes. German engine manufacturers attempted to reverse engineer specific Merlin design features, but the precision manufacturing requirements proved beyond immediate German capabilities. The tolerances required for Merlin production exceeded German machine tool accuracy by factors that would require complete retooling of engine manufacturing facilities. The investment required proved beyond German wartime resources. The supercharger technology incorporated in British engines represented particular challenges for German engineering teams. The complex gear ratios, automatic boost controls, and sophisticated intake ducting required manufacturing precision that German facilities could not achieve reliably. Multiple attempts to replicate British supercharger designs resulted in failures that consumed scarce engineering resources. Research programs initiated by German technical institutions attempted to develop equivalent manufacturing capabilities through intensive study of British production methods. However, the fundamental differences in industrial organization, workforce training, and quality control procedures required systemic changes that could not be implemented during wartime conditions. Spitfire production increased rapidly as British industry mobilized for sustained warfare. By late 1940, monthly production exceeded 150 aircraft, with output continuing to grow throughout 1941. German intelligence had grossly underestimated British manufacturing capabilities and industrial resilience. The British aircraft production system incorporated organizational innovations that German planners had not anticipated. The Shadow Factory program distributed manufacturing across multiple facilities while maintaining quality standards through centralized technical control. The approach provided production security against bombing attacks while enabling rapid expansion of output. Specialized tooling developed for Spitfire production enabled precision manufacturing of complex wing shapes that had previously been considered impossible for large-scale production. British manufacturers created hydraulic forming equipment, precision assembly fixtures, and quality control instruments specifically designed for elliptical wing construction. The tooling investment reflected long-term commitment to advanced manufacturing. Workforce training programs implemented throughout British aircraft industry created skilled craftsmen capable of working to tolerances that exceeded normal engineering standards. Government-sponsored training centers taught specialized techniques for advanced aircraft construction, while maintaining production schedules that supported rapidly increasing military requirements. Quality control procedures implemented across the British aircraft production system ensured consistent performance, despite increasing production rates and wartime pressures. Statistical quality control methods, comprehensive inspection procedures, and systematic testing protocols guaranteed that aircraft performance matched design specifications regardless of manufacturing location. The evolution of Spitfire variants continued throughout the war, with each new model providing enhanced performance that maintained British advantages over German developments. The Mark IX, introduced in 1942, incorporated a two-stage supercharged Merlin engine that extended performance advantages to extreme altitudes where German fighters could barely operate. The Merlin 61 engine installed in Spitfire Mark IX aircraft represented revolutionary advances in power plant technology that extended British performance advantages to altitudes exceeding 35,000 feet. The two-stage supercharger system automatically adjusted boost pressures and fuel mixture ratios to maintain sea-level power outputs throughout the operational envelope. Aerodynamic refinements incorporated in later Spitfire variants included pointed wingtips, improved cooling systems, and modified exhaust configurations that further enhanced climbing performance. These modifications, developed through systematic flight testing and combat experience analysis, maintained British technological advantages as German aircraft development struggled to achieve competitive performance levels. The Mark XIV variant, introduced in 1944, incorporated the Rolls-Royce Griffon engine that provided unprecedented power outputs while maintaining the aerodynamic advantages of Mitchell's original design. The combination of advanced power plant technology with refined aerodynamics produced climbing performance that exceeded early Spitfire variants by substantial margins. German responses included the development of new fighter aircraft like the Focke-Wulf FW-190 and improved Messerschmitt variants. While these aircraft provided better performance than early war German fighters, they never achieved the decisive superiority that Spitfires had established during the Battle of Britain. The Focke-Wulf FW-190, designed by Kurt Tank, represented German attempts to achieve performance competitive with British fighters through alternative engineering approaches. The radial engine configuration provided reliability advantages and acceptable performance characteristics, but could not match Spitfire climbing rates or high-altitude capabilities. German jet aircraft development, initiated during the Middle War period, attempted to leapfrog British technological advantages through revolutionary power plant technology. The Messerschmitt, Me-26, II and other jet fighters achieved impressive performance in some flight regimes, but could not address the fundamental tactical disadvantages created by Spitfire climbing superiority. The strategic air war over Europe demonstrated the lasting impact of early Spitfire advantages. German fighter units committed to defending against Allied bomber formations found themselves outclimbed and outmaneuvered by escort fighters based on Spitfire technology. The inability to achieve air superiority over German territory contributed directly to the collapse of German war production. Allied bomber formations escorted by Spitfire-derived fighters penetrated German airspace with increasing effectiveness as the war progressed. German interceptor aircraft struggled to achieve favorable engagement conditions against escort fighters that could outclimb any German aircraft. The tactical situation reversed completely from early war German advantages. The psychological impact on German fighter pilots extended throughout the war, as British and American aircraft continued demonstrating superior performance characteristics. Luftwaffe aircrew who had entered combat confident in their equipment superiority found themselves consistently outmatched by opponents flying technologically superior aircraft in virtually every engagement. Training programs for replacement German pilots incorporated acknowledgement of Allied aircraft superiority that would have been unthinkable during early war periods. German flight schools taught defensive tactics and survival techniques rather than aggressive approaches that assumed equipment advantages. The fundamental shift in training philosophy reflected realistic assessment of technological disadvantages. Post-war analysis revealed the full extent of German intelligence failures regarding British aircraft development. Luftwaffe estimates of Spitfire performance had been wrong by margins exceeding 50% in critical areas like rate of climb and high-altitude capability. These miscalculations contributed directly to strategic decisions that proved disastrous for German war aims. The intelligence failures stemmed from systematic underestimation of British engineering capabilities and industrial organization. German observers focused on superficial characteristics while ignoring fundamental advances in aerodynamics, power plant technology, and manufacturing techniques. The narrow analytical approach prevented accurate assessment of British technological achievements. Captured German documents analyzed after the war revealed the extent to which Spitfire superiority influenced German strategic planning and resource allocation. Luftwaffe requirements for improved fighters competed with other military priorities for limited industrial capacity. The technological challenge posed by British aircraft forced difficult choices that affected the entire German war effort. The technical examination of Spitfire design principles influenced post-war aircraft development worldwide. The elliptical wing configuration and advanced engine technology pioneered by British engineers became standard features in subsequent fighter designs. German engineers working for Allied powers after the war applied lessons learned from studying Spitfire technology to jet aircraft development. International recognition of Spitfire. Technological achievements influenced aircraft development programs in multiple countries throughout the post-war period. The design principles and manufacturing techniques developed for Spitfire production were studied and adapted by aircraft manufacturers worldwide. The influence of Mitchell's innovations extended far beyond immediate wartime applications. The psychological impact of Spitfire's superiority extended beyond immediate tactical consequences. German pilots who survived the war carried lasting memories of fighting against technically superior opponents. The confidence in German engineering excellence that had characterized pre-war attitudes never fully recovered from the shock of encountering British technological achievements. September 15, 1940. 26,000 feet above the English Channel. Flight Lieutenant Brian Carberry's Spitfire climbed away from Hauptmann Helmut Wick's Messerschmitt at 6,000 feet per minute, demonstrating the technological superiority that German pilots had been told was impossible. The aircraft they had mocked as an obsolete British design was proving decisively superior to Germany's best fighter in the most critical aspect of aerial combat. The psychological impact of this moment rippled throughout the Luftwaffe, as German pilots realized they no longer flew the world's best fighter aircraft. The confidence that had carried them through 3 years of victories evaporated as they watched British fighters outclimb their best aircraft with ease that defied explanation. The historical significance of this technological reversal extended far beyond immediate tactical implications. The German assumption of technological superiority had underpinned strategic planning for the entire European war. When British aircraft proved superior to German fighters, fundamental assumptions about industrial capabilities and engineering excellence required complete revision. Military historians analyzing the Battle of Britain have identified Spitfire climbing performance as a decisive factor that prevented German air superiority and made invasion of Britain impossible. The technological advantage provided by superior British engineering enabled a small number of Royal Air Force pilots to defeat larger German formations consistently. The strategic consequences of German intelligence failures regarding British aircraft capabilities influenced the entire course of World War II. Germany's inability to achieve air superiority over Britain preserved the British Isles as a base for eventual Allied operations against occupied Europe. The technological surprise represented by Spitfire performance contributed to strategic outcomes that affected global history. Contemporary analysis of declassified German documents reveals the extent to which Spitfire superiority influenced strategic decision-making at the highest levels of German leadership. Adolf Hitler's decision to postpone and eventually cancel invasion plans reflected recognition that air superiority could not be achieved against technologically superior British fighters. The economic implications of British technological leadership extended throughout the war as superior aircraft design influenced production priorities and resource allocation in multiple countries. Nations aligned with Britain gained access to advanced aviation technology, while German allies struggled with increasingly obsolete aircraft that could not compete with Allied developments. The educational value of analyzing German intelligence failures regarding Spitfire capabilities provides insights relevant to contemporary strategic planning and technological assessment. The systematic underestimation of British engineering achievements demonstrates the dangers of cultural prejudice and inadequate technical analysis in strategic intelligence evaluation. Modern military aviation continues to reflect principles established through Spitfire development and the German response to British technological superiority. The importance of superior climbing performance, advanced power plant technology, and precision manufacturing remains fundamental to contemporary fighter aircraft design and development. That's how German pilots learned to respect the Spitfire through painful experience that contradicted everything their intelligence services had told them about British engineering capabilities. The aircraft that had seemed like a joke became the symbol of technological achievement that would help determine the outcome of World War II. The lesson remains relevant today. Underestimating opponent capabilities based on preconceived assumptions can lead to strategic disasters that determine the fate of nations.